All right, silly people, here's the situation. We have a spinner, which I've denoted ket of chi uh, being equal to, in column vector notation, alpha, beta, um, where we have been provided some forms for alpha and beta equal to rho 1 e to the I phi 1 and beta equals rho 2 e to the I phi 2. And are meant to change this equation around so that it looks more like uh, equation 14.3.28a um, in this book. So that's gonna be cool. So the way to do this is to take the inner product of this guy first, which in theory should be equal to 1, so we can use that to constrain our values. So um, writing it all in column vector notation, that's going to be the complex conjugate of alpha as well as the complex conjugate of beta times this alpha beta column. That needs to be equal to 1. So when you take the inner product of that, you have alpha star alpha plus beta star beta equals 1. You can just say that this is alpha squared plus beta squared is 1. Um, and then what combination of squared things do we know give 1 every time? It's can be just a cosine and a sine, which is what the book was trying to get us towards. So it's sine squared theta over 2 and cosine squared theta over 2. Um, of course, you can use different combinations of cosine and sine, um, as well as different angles in there, but I'm going to use theta over 2 because that's what the book kind of wanted for this proof. So that's cool. Um, so that means that you can take rho 1 as being equal to cosine theta over 2 and rho 2 to be sine theta over 2, because remember this is this is just e to the minus I phi 1 rho 1 e to the I phi 2 plus rho 2. That's supposed to be rho 1 actually. E to the minus I phi 2 rho 2 e to the I phi 2, and so the complex bits get canceled out. See, this is definitely what rho 1 and rho 2 look like. So then we can rewrite our spinner in column vector notation as being cosine theta over 2 e to the I phi 1 sine theta over 2 e to the minus, or just e to the I phi 2 for now. And to make this equation look nicer, I'm going to pull out a factor of I phi over 2. And so you have cosine theta over 2 e to the I phi 1 over 2. And I'm actually pulling on one that is e to the I phi 1 over 2. Yeah, so then this thing, the second component, will be e to the I phi 2 minus I phi 1 over 2. You can also pull out a factor of e to the I phi 2 over 2. So that's going to look like e to the I phi 1 over 2 minus I phi 2 over 2 to look like cosine theta over 2 e to the I phi 1 over 2 minus I phi 2 over 2 sine theta over 2 e to the I phi 2 over 2 minus I phi 1 over 2. And then we can notice that this combination of phi 1 and phi 2 is the minus this combination of phi 1 and phi 2. So I can define phi equals a phi 1 minus phi 2 over 2 and write the spinner now as being e to the I phi times cosine theta over 2, we have e to the I phi, and then this is sine theta over 2, e to the minus I phi. And then the silliest part of this is um, because this constant on the outside is not a constant, but it is just a phase factor, which means it won't have any physical significance to the actual spinner, so we can just neglect it completely uh, and leave the spinner like this, which I think is what equation 14.3.28 reads. Yeah, it does. So this verifies the corollary that um, we were trying to do. Awesome.